Hello, working my way down here. We've got problem 14 using the binomial theorem. Great. And so the binomial theorem, of course, you can write it in its combinatoric form, or you can also just use Pascal's triangle, which to me is a little bit easier to just sort of write out the different rows here. It sort of depends on who you are, if you like to use the n choose k version or the Pascal's triangle version, but they're equivalent. So I'm going to do that. Let's see, did I do that correctly? Yep. And there's the fifth row. And so then these are going to be the coefficients of my cosine theta plus um, I sine theta. So we'll have 1 cosine theta to the fifth plus 5 cosine to the fourth theta I sine theta plus 10 cosine to the third theta. I'm going to be careful here. I sine theta is squared. I'm going to roll down to the next line. Plus 10 cosine squared theta. I sine theta to the third. Plus 5 cosine theta. I sine theta to the fourth. Plus 1 more I sine theta to the fifth. And the reason that I put this I sine theta powers in parentheses is just to remember what happens with the I squareds and everything like that. Okay, so that means that this comes out to be, let's see, I guess that's a correct answer, but we can simplify it a little bit more. I'm going to try to actually fit it all on one line this time. So we have cosine to the fifth plus 5 cosine to the fourth sine theta. Maybe let's stick the I on the end. And then this next one here, where cosine is to the third, this one here has an I squared, which becomes -1. So we go minus 10 cosine squared theta sine squared theta. And then the next one here, the I is raised to the third power, so that's a negative I. So I'll stick a -10 cosine squared theta sine cubed theta I. The next one is raised to the fourth power, which becomes a positive 1. So plus 5 cosine theta, 5 cosine theta sine to the fourth theta. And then the last one is to the fifth power, which is just the same as I itself. Sine to the fifth power theta I. And I think that's good. Okay. Next, part B. By using de Moivre's theorem and your expansion from part A, prove that cosine of 5 theta equals all that other junk right there. Okay. So de Moivre's theorem is that you can raise things to the fifth power, or that you can raise complex numbers to any power that you want. And what I want you to notice is that the original complex number here has an R value equal to 1. And so that means that we can think of our complex number as just being z equals e to the I theta. Therefore, z to the fifth is equal to e to the I times 5 theta. And then we can write that in that CIS format. In other words, it's cosine of 5 theta plus I sine of 5 theta. And that's what, let's see, that's what z to the fifth is equal to. And so my original expansion is this whole long line is also equal to z to the fifth, as well as this is equal to z to the fifth. And so what I should be able to do then is equate the real parts of those and equate the imaginary parts to prove the identity that I'm asked to find. Because I'm only asked about cosine, I'm only going to look at the real parts here. So I can say cosine of 5 theta is equal to the real parts. So I'm just going to circle the real parts in blue. Skip that next one. This one is a real part because it does not have an I. And this one is also a real part. Okay, so somehow we are supposed to make that come out to be the 16 minus 20 plus 5. That's interesting. Okay. Well, let's see what we can do. I'm going to give myself a little bit more space here. Come on, move with me. Okay. That's weird. Some of my things moved, some of them didn't move. Did not move. That's interesting. Okay, so cosine of 5 theta should equal that. So somehow I need to get rid of my sines here. Okay, that's good. That works. So all I need to use then is the idea that for any angle theta, sine squared theta plus cosine squared theta is going to equal 1. In other words, whenever I see a sine squared theta, I can replace it with 1 minus cosine squared theta. So I'm going to take those values and substitute it right in there for sine and right in there for sine as well. So then my real parts become cosine to the 5th theta minus 10 cosine squared theta times 1 minus cosine squared theta, because I substituted it for sine squared theta, plus 5 cosine theta 1 minus cosine squared theta squared, because it was sine to the 4th power. So we need to square that out again. And that's where we're getting some of those other values from. Oops, this was a cosine to the 3rd. Cosine to the 3rd. Okay, we're almost there, folks. And so that becomes cosine to the 5th theta minus 10 cosine to the 3rd theta plus 10 cosine to the 5th theta. And then if we square this out and distribute, we have plus 5 cosine theta, and then we'll have negative 2 cosine squared theta, negative 2, cosine squared theta, so that would be minus another 10 cosine cubed theta, and then we have cosine to the 4th theta, so plus another 5 cosine to the 5th theta. So collecting like terms then, I see we have 1 cosine to the 5th, 10 more cosine to the 5th, and 5 more cosine to the 5th. So that's 16 cosine to the 5th. Counting up my cosines to the 3rd, I have negative 10 here, negative 10 there, that checks out there, and 5 cosine theta checks out right there. So it took me a second. I actually thought I was going to get stuck, but then I was looking at the real parts. I knew that the idea is to equate the real parts of my binomial expansion with the real part of my de Moivre's theorem expansion. The part that hung me up for a second was seeing cosines and sines in my binomial expansion, and then realizing that the identity they asked me to prove only had cosines. And that's when the light bulb went off to go back and use this right here, the Pythagorean identity, And this is something that you can always use when you're dealing with angles, that the sine squared of an angle plus cosine squared of an angle equals 1. It comes from just doing the Pythagorean theorem on a arbitrary triangle within the unit circle. All right, so thanks for watching. There you go.